Now 13.1.5 is to do with the wave particle duality. So every time in the exams the students are faced with a situation where a particle, where you are being asked for the wave property of a particle or the particle property of a wave, right? Or the particle property of a wave, you need to be looking at the de Broglie's equation. Now the de Broglie's equation is lambda equals h over p. Lambda is the wavelength, okay, and p here is momentum. So you can see that momentum is a particle phenomena and wavelength is a wave phenomena, and both of them have been linked through one equation. So something with a wavelength can have a momentum, and something with a momentum can have a wavelength. Now 13.1.6 is outlining an experiment where the electrons were being, there was a diffraction pattern created from electrons which are considered traditionally as particles. So we know that electrons have mass, and yet they could produce a diffraction pattern because of the wave particle duality. Now next is solving problems using matter waves, involving matter waves, which would be using de Broglie's wavelength in problem solving techniques. 13.1.8, 9 and 10 are related to pretty much the discrete atomic levels that exist, in which electrons would exist. So the discrete energy states of electrons. So firstly, we'll talk about the electron in a box model. So you can see on page 10. Page 10, the postulate is that electrons are orbiting this atom in a standing wave. Okay, so electrons are behaving like a wave, and they are orbiting around the atom as a standing wave. And this standing wave has been equated to a one-dimensional standing wave, like for example a wave in a closed box which is of one dimension. Okay, so a one-dimensional standing wave for n equals 1. So we've covered this in standing waves. For n equals 1, the fundamental frequency, we have for standing waves with two closed ends, we have lambda n equals 2L over n. Okay, so from de Broglie's hypothesis we also have, so this is the wavelength of the standing wave that is set up by the electrons in an orbit. Now from de Broglie's hypothesis we have lambda equals h over p, right? And the kinetic energy can be written as half me v square. This is the kinetic energy of electrons. So okay, this is the kinetic energy of electrons, and so from here we can deduce that MEV whole square over 2n. Okay, MEV would be the momentum of the electrons, 2n. Okay, so we can just get the momentum in terms of the kinetic energy of the electrons, right? And over here again, since Ek equals p square over 2me, Ek is the kinetic energy or the energy of the electrons over here. When I substitute the value of p equals h over lambda n, right? And lambda n we know as 2L over n. So when we substitute that in Ek, we will finally get Ek or En. Okay, En would be the energy levels of the electron in orbit, right? So we would get n square h square over 8me L square. Okay, so the important thing to note that all these are constants, whereas n can take on discrete values of 1, 2, 3, etc. So therefore, this shows that the energy levels must be discrete and exist at discrete states like that. So this is basically showing that the electrons can, when they are modeled as a one-dimensional standing wave, they would have discrete energy states. Now Schrodinger's model and Heisenberg's uncertainty principle are closely related. So again, the students basically need a conceptual understanding of Heisenberg's uncertainty principle. The basic concept is that when you have an electron or when you have any object, the way in which an object is, how we see objects in nature is that photons would strike any object and then reflect back, and we would observe that in our eye, right? So this is how objects are observed in nature. But when we are talking about something as small as an electron, when a photon strikes it, the electron would move away, and therefore by the time the photon reflects and reaches our eye, the electron has already changed position. Okay, so therefore, now if I wanted to reduce the energy of the photon such that the electron does not move away, I would have to increase the wavelength. And increasing the wavelength, okay, we know that in order to resolve an object, I need to have a wavelength which is of the order of the magnitude of the size of an object. Okay, now therefore if I increase the wavelength, although the photon has less energy and therefore the electron will probably move lesser, we can only determine a large area in which the electron would exist. So, and conversely, if I had to reduce the wavelength and make the image sharper, the energy would be too high and the electron would move away. So at any one point, I can either accurately determine the position or the momentum of an electron. Okay. Therefore, there is always an uncertainty balance between the position and the momentum's uncertainty. So what Heisenberg's uncertainty principle states is that the uncertainty in position and the uncertainty in momentum, the multiplication of those will always be greater than a certain value. Okay. So how they get to this, and an explanation of the concept that I've just elaborated is on page 12, and basically that's the foundation of how we came across Heisenberg's uncertainty principle. So you can go through that with the students. Another form of Heisenberg's uncertainty principle is the energy time uncertainty principle, which also briefly you can skim through with the students. Again, what's majorly tested or the only main concept that they need to understand is why the position and momentum cannot simultaneously be determined for small objects like an electron. Now, using this, Schrödinger said that if we cannot identify accurately the position and momentum of an electron, then it does not make sense for us to determine accurate and discrete energy states like we just did with the electron in a box model. So what he did instead was that he defined the electrons with Schrödinger's defined the electron with a wave function. Okay. Now the wave function basically is a complicated function equated through by Schrödinger's equations, which we do not need to go into IV. All that the students need to know is that the wave function is defining electrons, and the square of the wave function will tell the probability of finding electron. Okay, the probability of finding electron at any particular point in space and time. Okay, so that means that we cannot describe electrons to be existing in a particular and definitive shape like this. So what, according to Schrodinger's model, is that the electron might exist, for example, for n equals 1, they might exist anywhere over here, with the probability of existence being higher in a certain region and then lower in another region. Okay? This here is also called the electron cloud model, and is currently the accepted model for electrons' existence in atoms and molecules. Okay, so this gives the Schrodinger's model for a hydrogen atom, and using the Schrodinger's model, there are certain discrepancies which were not being explained, for example, in the hydrogen spectra, and also the absorption spectra and emission spectra were only valid for hydrogen atoms. But using Schrodinger's model, we can not only accurately predict the hydrogen spectra, including the fine aspects which are mentioned here in 13.1.12, but also we can accurately predict the spectra of multi-atomic molecules as well. So that's a brief overview of Heisenberg's uncertainty principle and the Schrodinger's model. So again, the testing for these portions are more conceptual rather than numerical for Schrodinger and Heisenberg. So it's important that the students understand the basic concept and the underlying concept behind it. Now, moving on from here, we move on to 13.2, which is nuclear physics.